And recording is started. So thank you for joining. My name is Crystal. I am on the marketing team here at MIT Driverless on the business operations side. Today we have a lot to share with you, so I'm going to just get us moving and get us going forward. So next slide, please. So today's agenda is super packed. So we're going to start with some introductions by our team captain, then we'll move into sub-team project presentations, where we'll actually have each team talking about what they did over the summer. And finally, we'll wrap up with our Q&A. Some quick housekeeping items on the Q&A. Please, as you're going through and listening, if you have any questions for our team members, throw them into the chat. We will not be answering them as we are going. Instead, we'll save them for the Q&A, where we'll be going through the chat questions and answering them live. To figure out which room that you want to actually join for the breakout room time, please listen to the presentations, and based on where you want to join, use the Zoom functionality to indicate to us which room to put you in. So how you get there is at the bottom, you should see somewhere it says participants. Click that button, and there should be a pop-up that comes up or something else, like a sidebar that comes out that has these icons. Use these icons to tell us which one you want to be in. And then later on, we will be placing you come the top of the hour. So without further ado, I would love to introduce my friend and colleague, our amazing team captain, Jorge. Take it away, Jorge.
Awesome. Thank you so much, Crystal. Hello, everyone. My name is Jorge. I'm team captain for MIT Driverless. And I want to start off just welcoming everyone and thanking all of you for being here. Whether you are a sponsor, an advisor, faculty, staff, a follower, a fan of the team, or anyone, maybe a potential applicant interested in joining the team going forward, or just friends and family to someone else, to someone in the team. Thank you so much for all of your support on social media and just your involvement with the team and your fellowship throughout this journey that we've been in for a few years already. And thank you so much for being here. We're very excited to share all our summer progress with you. Everything our team has accomplished is definitely fueled by the support that we get on a daily basis from all of you following us. So we're very excited to share some of our progress with you. So what does our team do? Let me see if I can you move to the next slide? Oh, there we go, perfect. So our team builds high-speed autonomous race cars. That's essentially like our one-line description of what we do. It's a pretty fun place to be in. And in terms of our mission, MIT is a really, really cool place. It's a place where some of, very, very talented people are really working on solving some of the most advanced and cutting edge autonomous vehicle research problems out there. So by being part of the MIT ecosystem, what we're trying to achieve is, we know that there are so many centers and labs working on amazing research, and we definitely value that and partner with them. And we're so fortunate to have a lot of them as our advisors. But what we're really trying to make MIT Driverless become is the Center for Applied Autonomy at MIT. So the place where anyone who is interested in learning all those skills needed to succeed and be the future leaders of the autonomous vehicle industry, we want everyone who wants to gain those skills to think of MIT Driverless as a place they can go to develop those skills. So we are really trying to develop the autonomous vehicle leaders of tomorrow. And something that is very, very much embedded in our team's DNA from the start is just a collaboration spirit. And we want to learn from doing, but we also want to learn from our peers and from other schools and other students around the world doing the same things as we are. And that is pretty much the spirit of today's session, just to be able to share some of our learnings with all of you, get some feedback, get some questions, get some conversations going, and hopefully we'll be able to learn from all other teams and other companies and other people here in the event as well. So definitely building those relationships across campus and beyond the MIT campus is something very important for us as we develop the future leaders of the autonomous vehicle industry of tomorrow. Now, a little bit about our competitions. We Our team's origins are in the formless student category. We competed or were part of formless student for 2 seasons. And our next challenge is actually the India Autonomous Challenge, which is a new competition that just started a few months ago. And that is going to be racing next year in October 2021, so a year from now. And it's a really cool competition. We're going to be making an Indy Lights car autonomous, racing head-to-head against other amazing teams at no other than the Indianapolis Motor Speedway. So very excited about this. It's pretty much, arguably the most iconic racetrack in the US. So very excited about the opportunity to race there with other amazing teams. Crazy speeds, these cars hit almost 200 miles an hour. So making that autonomous, I think is gonna be pushing the limits of our team and other teams, making us learn a lot. And I think ultimately also hopefully getting some learnings that not only apply to us, but also help the industry in general. So we're very excited about this. We are working hard towards this challenge. And what we're gonna show you today is the progress that we've made over the summer towards this challenge. And we're also happy to announce that a couple of days ago, we also joined a second competition, which is the Rover Race competition. Again, super fast electric cars in this case, with some metaverse component. Very excited about going to that challenge as well. So Indy Autonomous Challenge and Rover Race are going to be our 2 challenges of the coming season. And what the team is going to be sharing with you today is basically 3 main things that we worked on during the summer. We have our architecture team who worked on defining several system architecture concepts for our autonomous vehicle pipeline. We have our perception team who worked on building a faster LiDAR for 3D object detection, and they're going to be sharing their experience with that. And we have our planning and controls team who worked on developing our first planner and controller for multi-agent racing, which is this is our first time dealing with multi-agent racing. So we're very excited about everything all the progress that we're making on that front as well. And finally, before moving on and getting started on the technical conversations of the different teams, just wanted to give a quick plug to anyone out there interested in our work. If you are interested in potentially becoming a sponsor or talking about sponsorship opportunities with our team, we have amazing sponsorship benefits that we have defined who are very valuable for industry partners. So if you want to become a sponsor, please feel free to email us at driverless-business@mit.edu. If you want to join our team as a team member, please, there's an application link here. Feel free to drop your application. We'll be more than happy to talk to you. And yeah, follow us on social media. We have Twitter, our Instagram, and LinkedIn as our main social media platform. So please look us up there and follow and share. And without further ado, I would love to hand it over to our amazing architecture lead, Nick, who is going to talk to us about how we define the architecture concepts for our pipeline. So Nick, take it away.
Hey, everybody. All right, so if you want to join the Q&A for the architecture team after the presentations are over, make sure to hit the no reaction button under your participants menu. So from the architecture team, it was a 3-person team over the summer. I'm leading the development, and I worked on perception, and TJ will also be presenting on planning and controls, and we'll dive a bit into what these things mean. Before we do that, here's a brief background of what the team's been able to accomplish over our first season of the Formula Student driverless competition, where our race car is able to essentially localize itself on an unmapped racetrack mapped by cones, and it can see those cones and drive around them and do so quickly. So we were able to do that. Now the question is, what's the difference when we move on to a different competition? Isabel, could you please first play on the video? So you'll notice the biggest difference right off the bat is the cars are going faster. The cars are bigger and stronger, and there's many cars all together at the same time on the racetrack next to each other. Very dangerous, very high speed, and requires kind of a different type of pipeline for autonomous software to be able to deal with this scenario. So we went through and kind of redesigned, using our past experience from ground up, what we think an autonomous vehicle software pipeline should look like for multi-agent high-speed racing with the Indy Lights cars. And the way we do that is we first figure out what are our high-level goals, what do we need the car to be able to do, and that comes from two things. One is the competition rules set some requirements for things we need to be able to do, and we also set some requirements for what we deem a functional car and what we deem a performant car, and what are the numbers we need to hit in terms of top speed, in terms of acceleration, in terms of frame rate for our perception models. And once we have those guiding principles, we start by defining the systems that we're going to piece together to get this thing to work. And for each of those systems, over the summer, we've made concepts for how could we possibly implement these systems underneath. And currently, we're at the concept selection phase, which is for most of the sub-teams, we are almost done picking exactly which concept we're going to be investigating for the rest of the competition. So here's the subsystem breakdown. We have perception, state estimation, and planning controls. We'll present on each of these briefly in the deep dive. Perception's job is to essentially use, in the example of the Formula Student case, use sensors such as camera and LiDAR. LiDAR provides a 3D point cloud. You'll hear more about that from the perception subteam later on. To look at where the other objects in the racetrack are and figure out where they're located and how they're pointing, which direction they're pointing. So collectively, location and heading or direction is called pose. So we want to get the object poses. We also want to get some sort of tag, which is another way of saying what class is this object? Is it an obstacle or is it another car? And if it's a car, do we know maybe what team is that car in, or at least some general visual features of that car, so that we can track it better. And finally, we also want to do drivable space segmentation. We won't talk about that too much. There's some well-known approaches for doing that. And to give you a sense of how we went about designing this perception pipeline, is we kind of broke down all the different sensor modalities, and we'll only dive into monocular camera object detection. So we have 5 cameras pointing in different directions around the vehicle, and we want to detect where the other cars are on these images. And then we want to convert that detection on the image space to a location on the racetrack relative to the car. And there's many different ways you can go about designing a model, particularly a neural network-based model for achieving this goal. Dimensionality-wise, first thing you can do is, well, you have 5 sensors. Do you want to give the 5 images to one big model, or do you want to have one small model and give that a model one image at a time? So do you want to give the images jointly in a wide model, or do you want to batch them up and run them through basically one at a time? You also have some other information in dimensionality, such as time. So do you want your model to only see the current frame? Do you want it to see the past few frames? Or do you want to use some more recent research approaches, like the temporal shift module that came out of MIT's hand lab, which we're collaborating with in this challenge? And then how do you want to find the objects in the scene? Do you want to do instance segmentation by painting each of the pixels, or draw bounding box around them. And finally, once you know where the object is in the image, you also need to know where it is relative to the car. And there's many different ways to go about that. Feel free to ask us in the Q&A session if you want to deep dive on that. I'll also go over the state estimation architecture for Bokeh. State estimation is essentially, well, trying to estimate the vehicle's state, and state is contains several things. So first, it's about where is the current car. So where are we? Where's the vehicle where our agent is trying to drive? And first, and you kind of break that up into two components when we did the concept analysis. First, you want to do local estimation, which is how are we moving over time, and we want kind of like a velocity estimation. And finally, we also want to know, using that, where are we on the racetrack? So we don't just want to know how we've moved since the car was booted up on the racetrack, but we want to know exactly where we're on the racetrack, whether a corner is coming up, and so on. And finally, to aid the planning and controls team in knowing where the other vehicles are and kind of projecting the behavior of the vehicles and where they're going to go so that we can avoid collisions, we also need an object tracking component, which is for detecting and displaying the trajectories of all the other vehicles based on the perception input. So state estimation overall takes in sensors that are well known in the AV industry, such as IMU, GPS, and wheel speeds, in addition to a map of the racetrack and the object detections from perception. And it spits out the velocity, the pose of the vehicle on the racetrack. Pose, remember, is position and heading, and also the trajectories of all the other objects in a format that planning and controls will be able to read. And the split comes really naturally from here. We have a velocity estimator, and examples of velocity estimators are an extended Kalman filter. There's been some recent papers on RNN-based, recurrent neural network-based velocity estimation. And you can take that, and that's already one of the outputs. And then you pass that velocity to a localizer that uses velocity in addition to other features, such as visual features from the camera and the LiDAR, to actually localize us on the racetrack. And finally, now that you know where you are on the racetrack, you can convert all the object detections from perception into a mapped view of where all the objects are. And now the job is of the object tracker is to figure out which object is which and like what are the trajectories from there. So kind of an intuitive example for object tracking is, if you look at this image, the time axis, which goes downward in this example, and the space axis in one dimension goes to the right, we have the red car and the green car, and we see them both moving forward over time. And say we know in time 1 and time 2 that the red car is there and the green car is there. What we can do is project their velocity into time 3, and then look at our object detections, which are currently not labeled, they're not part of the trajectory, and ask the question, which car is more likely to be the green car and which car is more likely to be the red car? And it's not as simple as just doing this line, but in 3D, but rather you also want to use probability and maybe also the object tags to make sure that you're disambiguating between cars that are actually racing really close and wheel to wheel. So that's something we will be exploring and developing over the rest of the competition season. Now I'll hand it over to TJ, and he'll go over planning and controls. Okay.
Right. Thank you, Nick. Following the same systems thinking methodology, what are the high-level goals for planning and controls? Well, we need to win. That's our primary goal. But for winning, we need to finish the race, and we need to finish the race without colliding with any of the other cars. these cars are going at or upwards of 150 to 200 miles per hour speeds. So these are extremely high speeds, and things may or things will fail. So if there's a collision, things can get really messy. There is a risk of injuries. There is a risk of financial loss. These cars cost a lot. So safety is very important, and that's why we took a top-down safety-centric approach to architecting this system. So these high-level goals of finishing the race and avoiding collisions can be sort of broken down into 4 primary objectives. The first objective is system performance. Basically, it means that what we need to do to achieve the accelerations and speeds that we are talking about. Second is trajectory planning and motion control. So basically, it means that to plan a trajectory to avoid collisions and to control the motion of the vehicle on that trajectory so as to finish the race and win. The third is fault handling and safety and diagnostics. So things will go wrong, and in anticipation of that, how can we architect our system to mitigate the failure modes and to recover from those failure modes? That is also extremely critical to be aware of, to be designed for. And fourth primary objective would be communication with the Deep Orange interface. And to give you a little bit more information about Deep Orange is basically a standardized name of the actual vehicle that we will be using in this Indy Autonomous Challenge. And the race conditions require us to be aware of what the control commands are coming from the control room, and then act upon those commands as needed. So before I go down deeper into how these primary objectives were designed or were architected for, let's look at the system. What the planning and control subsystem looks like, and what are its boundaries and interfaces. So on this slide, you can see the red block, the red box as planning and controls, and it talks with state estimation, Deep Orange control room, and it could optionally talk with the perception subsystem as well as directly to the sensors. The status estimation, as Nick mentioned, gives the position, velocities, accelerations of our car as well as of other cars, so that we can make intelligent decisions on how to navigate the racetrack. The Deep Orange control room would give us inputs on if we need to transition to a certain mode, or if the control room wants the vehicle to transition to a certain mode, if the vehicle wants to enter a pit stop or exit a pit stop. Those kind of decisions have to be taken using those inputs from the control room. And optionally, this subsystem can also take inputs directly from sensors or from the perception subsystem. And why this is important is because it would add redundancy. For example, let's say if the state estimation fails, then the planning and controls won't have any idea of where the self vehicle is, as well as where other vehicles are. But if it's getting data directly from sensors and directly from the perception subsystem, then it can kind of make a guesstimate of where other vehicles are and recover from this failure mode and still keep driving, either gracefully quit the race or reset the state estimation and then continue the race. All this processing happens inside this red box, and out comes the steering angle, the accelerator pedal command, and the brake pedal command, which goes to the vehicle so as to drive the vehicle. So to achieve this and to achieve all the primary goals and objectives that I mentioned earlier, we debated on a variety of different concepts, and we sort of narrowed down on a concept which is abstract enough. And this concept has 3 different abstract subsystems. One is the planning subsystem, one is the control subsystem, and the third one is the supervisory controller. So the planning and control subsystem both have a primary control algorithm, which will do trajectory mapping, which will do all the planning, path planning, and which will do all the controls to calculate the steering commands and acceleration commands that needed to be sent to the vehicle. But it would also have a redundant, more deterministic controller for each planning and controls in the case where the primary logic fails to compute a good value. And these primary controllers are highly optimized controls, such as, say, model predictive control or more advanced control algorithms. So these, in some instances, could crash. These could give infeasible results, or these could give results which are impossible to achieve while driving the vehicle safely. So in these conditions, if such things happen, then a secondary redundant controller would take charge. And this is a more lightweight deterministic controller which will always output a trajectory or a control command. It need not be optimal, but it would be enough for the vehicle to navigate safely on the track. And if this continues happening, if the primary controller keeps failing, then we should have some way to gracefully quit. And this is where the supervisory controller comes into action. So the supervisory controller really takes the other two primary objectives, which are mentioned on the top right corner, the fault handling and the communication with the control room. So the fault handling, if let's say these planning and control subsystems keep on failing, the way the vehicle should gracefully quit is such that the vehicle can go into a limp mode, the vehicle can go off the racetrack and then stop instead of instantly quitting on the racetrack itself. So all these fault handling diagnostics and safety nets will be placed on by the supervisory controller, and this controller will also talk with the control room to detect any transition, any input commands that the control room wants the vehicle to work on. So this abstract subsystem will also give teams an abstract nature to independently work on these subsystems and then integrate it when they are ready for integration. And so I have been talking a lot in more abstract terms. There are a lot of black boxes, red boxes, orange boxes here, but you will get into more technical details as our subsystem team leads start talking about perception, planning, and controls. So without further ado, I would like to hand it over to Sibo, who is going to go over the technical details of perception.
Yeah. Hello, everyone. Welcome to Perception. And if you would like to learn more about our work, remember to hit the slower button. Well, it's just the button means slow. We are pretty fast. And I'm Sibo, co-leading the perception team with Zhijian this summer. And our very awesome perception team also includes Sophie and Matthew. And this summer, we basically have two main goals. And I'll let Zhijian talk about the first one.
Hi everyone, I'm Zhijian, and I'm going to first give you a brief introduction of what the perception team does. Basically, the perception team is the eye of the autonomous vehicle. So for this system, it has two different sensors on the car. One is the camera sensor, one is the LiDAR sensor. So the camera sensor basically captures the RGB images, and the LiDAR sensor captures the 3D point cloud. So in order to utilize the information from both sensors, in this summer we are working on to replicate one state-of-the-art fusion model called point painting, and this part is mainly done by Matt, and I will let Matt to describe what we have done on this part.
Thank you, Zhijian. As you just mentioned, over the summer, I replicated a research paper from Aptiv that achieved state-of-the-art results in 3D object detection by discovering a novel way to perform this multi-sensor fusion. More specifically, is a method where information from a camera is inferred from the camera is combined with a LiDAR point cloud to improve performance in that task of 3D object detection. And I will now walk you through each of those three steps. Here we go. So the first step is inferring information from a camera. So we do this by taking a camera image and inputting it into a model that has learned how to downsample that image, then upsample the image such that the resulting image the pixel values in that resulting image correspond to a score of which class of object that pixel belongs to. For instance, this pixel might belong to the class tree, or this pixel might belong to the class road. So more specifically in this task of 3D object detection, we're actually only concerned with the information, the pixels that pertain to three classes: the car, the pedestrian, and the cyclist. So from here on out, we are actually only going to, when we talk about using the information inferred from the camera, we're actually only going to use the values from those classes of pixels. So the next step, after we get information from the camera, is to then fuse the LiDAR point cloud with that information from the camera. Now, an important prerequisite of this step is that sensor calibration has been performed, such that we know how an X, Y, Z points in the LiDAR point cloud can be mapped to the X, Y pixel in the image. And so the data set that both the researchers from Aptiv used for one of the data sets they used for their paper, as well as the data set we used for this, provided us that calibration so we can use that mapping. More formally, we use that mapping to execute two types of transformations. One is a homogeneous transformation. Another is a projective transformation on that 3D point cloud to project it into that 2D image that you see sort of in the top middle of the screen. Once we've done that, you see how nicely that lines up with the semantic segmentation mask, those pixel-wise class scores on the bottom. We can then concatenate the two, resulting in that painted point cloud you see on the right. Notice how the car now has the points pertaining to the car have now been painted blue. So I made a video showing. So obviously, you know, our visual system is different than like how we program a computer's visual system to be, but you can sort of see how in that middle image, how much more clear those objects of interest, the cars, the pedestrians, the cyclists, stand out as compared to the normal LiDAR point cloud once we've taken that information from the camera and appended it to the point cloud. The third and final step was we then take that painted point cloud, and then we develop or train a 3D object model to learn how to detect objects in that 3D point cloud. So as inputs, we have our painted point cloud, and as outputs, we have the not only the class of the object, is it a car, is it a pedestrian, but also where is it oriented in 3D space in that point cloud. And you can sort of see the label car and those 3D bounding boxes around those green points of the car. So when we were implementing, when we were replicating this research, we wanted to do 3 runs. We took a model we had and trained it on the normal point cloud, no augmentation, saw how that performance was. We then create our painted point cloud, right, with fusing the two sensor modalities together, and looked at those results. And then we took that and compared it to the results from the paper, and we were able to match their replication numbers. So in conclusion, putting this all together, we made a little video here. We have in the middle that range view. This is sort of the car's perspective of the LiDAR points. We have on top the bird eye view, and on bottom we have the camera view, and we have our prediction boxes around the top too. And yep, that was our work, and really looking forward to continuing working on this. And back to you, Sibo.
Yep, thanks. And yep, as we already learned from Nick and Zhijian that we have camera and LiDAR as our main sensors on the vehicle, where LiDAR operates 10 times per second and camera operates 37 times per second. For usual road self-driving car, which runs at probably 50 miles per hour, this combination is totally acceptable. However, for super fast racing vehicle, which runs at probably 200 miles per hour, this is unacceptable because we have too much time of blind. As LiDAR is one of the most accurate sensors, we definitely don't want to miss this in our perception party. So to tackle this challenge, we are inspired by the high operating frequency of camera and want to combine it with our LiDAR. And therefore, building a faster LiDAR. And this is our second goal of this summer. And with this idea in our mind, we want to employ the advantage of camera runs 3 times faster than LiDAR, using an efficient predictive model to create the future LiDAR point cloud, and employ camera information to help correcting the LiDAR predictive model. And at the end of the day, ultimately, we wish we can fill in the void between LiDAR frames and make LiDAR as fast as camera. And Sophie in our perception team is leading the effort of developing this efficient and accurate 3D point cloud predictive model. And I'll pass the torch to her.
Hi, everyone, and thank you, Sibo. So as Sibo mentioned before, we are trying to fill in the gap between the LiDAR and also fuse the camera information. So the point cloud data are showed. Here we have this point cloud data, and it's shown in the bird's eye view. There is a red point in the middle to represent our Eagle vehicle, and the X and Y are the horizontal coordinates, and the Z is the vertical coordinates. We only represent a front-facing camera here for a better understanding of our design, and we have our LiDAR point plotted as color dots scattered on the RGB image on the right-hand side. So our first step is to get the corresponding color in the RGB image for each point cloud coordinates as our model input. As we can see here, we are using the RGB image and the corresponding point cloud data in the same time frame to get the projected point on the right. And then we extract the RGB color from the image for each corresponding point cloud coordinates. Next, we have a sequence of the camera and point cloud data. So we can tell that in the camera image, we can tell that the vehicle is moving forward. And for each camera, we have a corresponding point cloud frame. Our model now takes in a continuous series of camera and point cloud concatenate data as input to predict the future frame. We have developed 2 models here. One is to use single image point cloud data as input. The other one is to use double image point cloud data as input. We use MSE and FPS to measure the performance of our model. FPS means frames per second. In our case specifically, it means the inference time to process each LiDAR and camera frame to predict the future frame. So presumably, the higher the FPS, the better the model's performance. And MSE means mean square error. We are using the predicted point cloud coordinates and ground truth point cloud coordinates to calculate the mean square error. In the worst case, when our prediction and ground truths are entirely misaligned, the mean square error can go to infinity. However, as we can see here, our model has very impressive performance in terms of mean square error. For the single input model, the mean square error is around 1.86. And for the double input model, the mean square error is about 1.06. As a result, when we have more previous information for our model to learn, the model clearly performs better. However, when our model needs to pre-process more data as input, it slows down the inference time. So we can see here, the single input model has higher FPS compared to the double input model, but both models can fill in the gap between our ground truth point cloud because the prediction has higher FPS than our ground truth LiDAR point cloud frame rate. So we can get future LiDAR data beforehand to interpolate the intermediate LiDAR points between 2 ground truth LiDAR points. We are still working on finding the best balance between accuracy and efficiency. Other than this, we still have a lot of magic tricks to increase our model's performance. And here we have our fantastic visualization video to demo our double input model's performance. The blank space is the driving road, and our Eagle vehicle is still in the middle of the point cloud, and the vehicle are driving toward our right-hand side. The left side is a sequence of ground truth point cloud, and the right side is the prediction point cloud. As we can see, our model can learn pretty much the whole key point of the ground truth point cloud. In the future, we plan to use more historical information to predict future frames. Say we use 8 frames of camera data and LiDAR data in the past to predict future 8 to 14 frames. Also, we plan to improve the efficiency of our model for the Indy Autonomous Challenge. We plan to convert the framework to C++ for faster inference. We also want to do neural network pruning. In the end, we want to do int8 quantization. And that's all from my side. I'll pass it to Sipo.
Thanks, Sophie. So that comes to our path forward for Perception team, and hope you guys enjoyed our presentation already. And for the future improvements, what we can do first, like actually use more camera frame to correct our 3D predictive model. And second, as we have already have our 3D and 2D object detection model, we will explore the option of developing multi-agent object tracking. And third, we will explore the option to develop dual redundant perception system so that when one sensor is down, another sensor can still do perception independently. And we're looking forward to do that. And I guess we'll pass the torch to planning and controls.
Thanks, Sibo. So I'm Adam. I'm the controls lead for planning and controls. That should be going to the next slide. Thanks. So the high level goal of our team is to take all that incredible information about the environment and where we are from perception and state estimation and use that to create a safe and preferably fast path around the track that avoids all collisions. The controls team's goal is to take that path and to convert that into steering and acceleration values to get to the car in order to follow it as accurately as possible, to the best ability of the vehicle. Can you go next slide? So here's kind of a high-level overview of how our system is currently set up. So you can see we get information from state estimation and perception, as well as what race mode we're in order to decide whether we have to head back to a pit or other things like that. So the planning side uses a handful of different methods to very quickly create trajectories that avoid all the obstacles that we can see on the track. So we use a pre-computed cost to go. Because we already know what the track looks like, we can make some optimizations offline in order to save time on the road. And we combine that with agent models using perception data about whether the vehicles are in order to create paths that avoid obstacles. That combined with a velocity profile planner to give a good guess on what speed we should be running at creates a trajectory that's then passed on to controls. So in this case, planning makes the high-level decisions like what direction to go down the track, whether you pass cars on the left or the right, how you're going to maneuver around obstacles, while controls has more advanced models of the vehicle and can thus make more minute changes to optimize how we control the vehicle to be going as fast as possible. So that's what the multi-agent MPC or model predictive control does. It takes information about the agent models in order to help avoid obstacles, and then will tweak the trajectory in commands in ways that optimize our speed while still avoiding the obstacles. Now, in case that fails, in parallel, we have a feedback controller so we can guarantee that the vehicle can always be controlled safely. So to explain the planning further, I'm gonna pass it on to our incredible planning engineer, Mike.
Thanks, Adam. We pop to the next slide. Awesome. So as Adam mentioned, the planning stack really has two goals, right? So the first is to make the car go as fast as possible. And the second is to do that as safely as possible, meaning avoiding obstacles, namely other cars. To do this though, there's a few system constraints. So as has been mentioned a few times, we're moving at really high speeds. So, looking at every 1/10 of a second, that means we're potentially moving as far as 8 meters. There's several vehicle dynamic constraints that we need to take into account, and then also all of these other obstacles, moving vehicles, and predicting their future trajectories as well. So what we've kind of settled on here is using a graph-based planning approach, and this is heavily inspired by some of the work done by Technical University of Munich in their work with RoboRace over the past 2 seasons. There's several other options that we considered out there. So there's been a bunch of work done by Stanford and by Berkeley using some optimization-based approaches, also in the race car racing space. And then there's quite a few heuristic-based approaches out there as well. But what we decided was the graph method is pretty efficient because the track is known and well mapped, and in this case reduces a lot of the variability. We're able to keep that in memory and use that to plan off of. So overall, the pipeline shown here takes in all these different inputs and communicates with all the teams that Adam mentioned previously. And the pipeline itself is broken down into basically 2 major components. There's an online component and an offline component, really in the other order. So if we could move to the next slide, please. Great. So the cost to go map, this is the offline component. And the general idea here is that we're taking the well-known mapped IMS track and discretizing it using a Frenet frame-based lattice. Discretizing around the midline, we're using variable longitudinal separation of points based on the track curvature at different points on the track. And we're computing all of the C1 splines, essentially. So non-curvature continuous, but just splines between each point. And we're assigning costs to each of those. And those costs are a function of both the curvature and also the deviation, the lateral deviation from the optimal racing line, which is known and computed for our specific vehicle dynamics. And then this overall graph, as I mentioned, is held in memory. So right now, less than 100 megs, but depending on the discretization. And so then with that, we can move into our online portion. So next slide, please. Okay, so there we go. Perfect. Yep. So the online segment basically starts with extracting a local section of our overall track graph based on the current location of the vehicle and a fixed planning horizon. So that extraction would be something like is shown on the right there. That's a little bit stretched horizontally so we can see what's going on. And then we go and with our inputs from our multi-agent model and our perception, we're able to identify and localize the obstacles on the local graph. We're using node-based and edge-based deletion to remove sections of the graph where there are obstacles. And then we go ahead and trigger a minimum cost path search and finally generate our curvature continuous trajectories and our velocity profile. And that's all sent on to the low-level controls portion. So right now, our current runtime latency is a bit under 50 milliseconds. A lot of the time is taken up with collision checking. So that's definitely one of the areas we're looking to optimize in the future. And then on the right here in the video, you can see kind of what everything looks like when it's put together. This is running with static obstacles right now. And as we further develop our multi-agent model, we'll have this running with other moving vehicles and dynamic obstacles as well. So upcoming in path planning, if we could just move to the next slide. So a few things we're super excited to continue on, further developing the higher level like agent planning models, as well as our our kind of strategic race framework to decide, whether we want to pass right or pass left or make defensive maneuvers. That will kind of feed into how we're thinking about building out the different trajectory options that exist within each planning time step. And then finally, integrating this with all of the rest of the team's work. Definitely still some work there to do and get this tested in simulation, but super excited to continue on with that. So with that, I'd like to introduce Arjun, who's been leading our work on multi-agent modeling over the summer. Thanks.
Hi, everyone. I'm Arjun. This summer, I split my time between the agent model portion of planning and controls and also working on getting a simulation environment for the India Autonomous Challenge up and running. The two main high-level goals with our multi-agent model were to provide the multi-agent model predictive controller with a hard collision constraint for the other vehicles on the road, and then also provide obstacle avoidance in the form of a probability occupancy ellipse to represent where the other vehicles are. So we want to have a hard constraint for model predictive control, and then we want to have a continuous function so we can assign or get the probability that the vehicle is in that spot at any point. So the first step in creating our vehicle model was to decide, what do we want to account for? And so the biggest thing is, because this is such a high-speed race, we want to be able to account for the changes in our uncertainty of where our guess is for the other vehicles over time. So we'll take the delta between the system time and the observed time of the object and use that to create a model for the growth and uncertainty, which we can then plug the current system time into to create a Gaussian distribution for where we think the other vehicle is likely to be. So the mean for this Gaussian is the pose of the other vehicle, and the covariance would be the variance for the bivariate Gaussian distribution. So the key considerations we have are growth and uncertainty over time. We also want to account for the lane keeping likelihood of vehicles during the straightaways, and we also want to have the ability to determine and create the bounds and collision constraints for MPC at an arbitrary level of confidence. So we want to say we're 3 sigma or we're within 2 sigma confident that the vehicle is within this bound. So the ingredients for the agent model recipe first started with creating a model for growth and uncertainty, and then once we have create a Gaussian from that, we can solve for the level sets of the Gaussian at arbitrary levels of confidence. And then because bivariate Gaussians, the level set solved to ellipses, we can use those ellipse coefficients to add to the actual the major and semi-major axis length of the other agents. So you can see in the picture in the bottom left, it shows the kind of the minimum shape of the vehicle, and then it shows the expanded model based on the growth and uncertainty in between the system time and our observed time of the vehicle. So now how do we actually create a collision constraint for our model predictive controller? So we're using a Minkowski sum to, or first we're representing our ego vehicle as a series of disks. We don't want to use an ellipse for our ego vehicle because it'd be really hard to calculate the Minkowski sum between 2 non-axis aligned shapes. So we're using circles so we can calculate the Minkowski sum between the other vehicle ellipse and the 4 disks that represent our own vehicle. This also allows for much quicker Minkowski sum computation as opposed to trying to do non-axis aligned shapes. This model also has a twofold benefit because it allows us to create a probability density function for where we believe the other road agents to be. If you can go to the next slide now. Okay, so now that we have an occupancy probability ellipse from the Gaussian distribution and the agent model, we can actually feed the probability density function into our obstacle avoidance. And if we want to in the future, we can assign costs for nodes based on the probability that a vehicle is there. And you can see in the picture that we show we show the ellipse coefficients for different levels of confidence. So I think that shows four different confidence levels. And you can see kind of a zoomed in picture that shows what it looks like once you've actually added the cost of these different points to a graph. So where the red points, it's more likely that the other vehicle is there, and the white points, it's less likely that another vehicle is there. What's next for me is to work on integrating our agent trajectory prediction with our agent model. So how do we take into account the future states of the vehicle to kind of path plan around? And can we develop a more optimized ego vehicle representation? Oh. So yeah, can we design a more optimized ego vehicle representation with maybe higher resolution so we can perform more complex maneuvers with the cost, of course, being performance. And then, of course, I have to test and integrate with the rest of the planning and controls team, and then also perception and state estimation. I'm going to hand it back to Adam so he can do a deep dive into controls.
Thanks, Arjun. So I'll just quickly go over what the control structure looks like, as we briefly mentioned. You can see we have the model predictive controller and the backup controller in parallel for robustness, taking inputs from the trajectory from planning, as well as the current state from state estimation. And we're producing acceleration and steering angle commands. And we have a couple other things in line here, including a controls check to make sure that everything we're sending are safe values, as well as a trajectory sampler so we can produce control signals at a higher fidelity than at the rate that MPC runs. And you can see inside of MPC, we have a dynamic model, which is forces based and has a model of the tire, as well as a kinematic MPC that's a more geometry based model and more stable at low speeds. And depending on whatever speed the vehicle is running at, we'll use one of the two or both of them in some hybrid region in order to make it stable at all speeds. You get next slide. So in order to run this MPC, we use this really, really powerful nonlinear solver called Forces Pro. And we set up the problem in the solver by initializing at the current state of the vehicle and having a discrete time horizon, in this case 3 seconds, in which the solver will use some model of the vehicle as well as certain constraints and a cost to essentially follow the trajectory as well as possible by optimizing over all the dimensions of the states times the discrete time in order to converge on optimal controls for whatever input trajectory you give it. So we have a couple options on how to represent that trajectory. So an easy option is position following, where the trajectory is passed as an x of t and a y of t. And at a given time, we're always chasing some point in the trajectory. However, we want to give MPC a little more freedom than that. And we decide to prioritize following the path over following the position. So in this case, we may be, even if we lag along the path, we know it's more important to follow the shape of that path. And we do this by representing the trajectory as a series of points and velocities parameterized by the arc length of that path. And to get an idea of what we're optimizing, you can see our cost function at the bottom. We're using the cross-track error or the lateral error and the lag error, or the longitudinal, as well as the velocity in order to track that trajectory as well as possible. But we also have this velocity component where we reward going faster. So this means that while we do get an input trajectory, we're designed to deviate from it to a certain extent if it means that we can go faster. And we do this because we have this advanced model of the vehicle that allows us to really push the car to its physical limits. Next slide. So you can see some work that we've done here so far and some progress on developing the software. In the first path, you see the blue line, which is our trajectory that we've been given, the orange line, which is the path of the vehicle, and the orange dots, which are where we think we are in the path. So in the first case, we're given a feasible trajectory where we follow the path very well, having a good model of the vehicle. But in the second, we're giving an infeasible trajectory. And instead of giving dangerous commands in order to try to follow that trajectory, you can see the vehicle follows it to the best of its ability, still creating a safe path. Next. So one characteristic of a nonlinear solver is the runtime is indeterminate. Based on whatever parameters we give it, we don't actually know for sure how long it can run. You can see between that, right now we have a 50 to 60 millisecond runtime, but we're confident we can get that down to 30 to 40 milliseconds. And in order to make this safe, we have a max iteration cutoff so that over a certain runtime, we can cut off MPC and resort to using that backup controller, which is essentially a gain scheduled PD controller, so that no matter what happens to MPC, we can still be confident that the car will be able to operate. And then one more. Or next slide. Yeah. So some constraints that we put on this model are making sure that we don't collide with other agents, as well as making sure that our slip is low enough and the vehicle doesn't slip out of control. So that's based on the model. And these are all implemented as slack constraints, so we know that the model is still going to solve. So some upcoming exciting things for controls. Delay integrations. So for MPC, you have to essentially forward simulate the current state if there's a delay on the actuators, which there almost certainly is. Reinforcement learning for a better model. So we have our model of the vehicle, but things change, tires get hot, the track changes as you do many laps, your fuel consumption changes. So using reinforcement learning and a log of previous states can help us to optimize for a better model in real time. So we really are pushing the vehicle to its max. Taking things like tire wear and fuel consumption, these local level optimizations into account can be useful, although any higher level optimizations we'd be done with planning, as well as more advanced agent states. So implementing that with MPC and getting more advanced behavior and taking that into account for how we deviate from our trajectory. So with that, I'm going to pass it on to Crystal to finish up the meeting and help us launch into some exciting Q&A.
Awesome. Thank you, Adam. So now it's time for the Q&A, but I have a couple just kind of quick housekeeping things to wrap things up for us. We're not going to come back for any sort of wrap up, so this is effectively the wrap up. So as you feel ready, feel free to leave whenever you want. To some of the questions about the Q&A, general and architecture, we realized it made sense to just merge into one, so that will be one room. Please make sure to indicate which room you would like to join. Like I said, going into the participants tab and then indicating with the icons below as based in the slide here, like the icon indicates which room you want to join. Give me a second to get you into those rooms after we open them. If you would like to change rooms, you are totally free to do that. All you have to do is leave that breakout room, but not the meeting. Stay in the meeting, don't leave the meeting, and then come back to the main room and we can reassign you. Just let me know where you want to go. We are recording this meeting as well as the breakout rooms. So we will be sending these out afterwards with timestamps if you want to figure out a question that you had asked, you're worried that you missed it, we can definitely point you to the right place. And finally, of course, thank you so much for attending. Like we said before, if you want to join us, if you want to sponsor us, if you want to follow us, we'll be in the recording email. I will also be following up with all those links to the things that we talked about before. So now I'm going to launch our breakout rooms. And like I said, give me a second to get you all placed in the right rooms.